Okay, so hello everyone again. This is lecture number 7 from the chapter System of Particles and Rotational Motion. In the previous discussion, we have started with a concept which is called as your principle of moments. I will first revise it quickly and then we can move on with the next discussion. Okay, so this is lecture number 7 from the chapter System of Particles and Rotational Motion. I am Samir Lawankar. Let's begin our discussion. So currently we are on the 8th subtopic, that is your equilibrium of a rigid body. We have completed with the introduction, center of mass, motion of center of mass, linear momentum of a system of particles, vector product of two vectors, angular velocity and its relation with linear velocity, and torque and angular momentum. Fine. So let us understand what is this equilibrium of a rigid body, and then let's move forward. So these all things have already been explained in the previous classes. Let's today understand again. Yes, so principle of moments. So finally what we got in the last discussion was that the above equation, so basically this equation is basically called as your expresses the principle of moments of a lever. Okay, so this equation, let me change this equation a little bit. So if I put F1 on the left hand, F2 on left hand side, and I write D1 on the right hand side, what I basically get is, so basically what was the equation? The equation is F1 D1 is equal to F2 D2, right? So this equation can also be written as F1 by F2 is equal to D2 by D1, correct? Okay. First of all, remember that this ratio is also called as, this ratio is called as mechanical advantage. Right? Okay. Now let us try to understand about this. Okay. So now let us say that if this value of D2 is larger than D1. So let us take the first case. So if D2 is greater than D1, then what we can say? We can basically say that F1 is greater than F2, or we can say F1 by F2 is greater than 1, or basically we can say that the mechanical advantage is greater than. Okay. So what does it basically mean? It basically means that a small effort can be used to lift a larger load. Okay, so if we are, if you remember correctly, what was the effect? So basically F1 was a load. So if we need to calculate, or if we need to find, or basically if we need a smaller force, so that we can lift a higher force, we can basically implement a distance D2 which is greater than D1. So if we basically find this condition, so we can basically implement this condition. That is, we can reply with basically a smaller force is needed to lift a higher value of F1. Okay, so I will just write what does it basically mean. It basically means that a small effort can be used to lift a large load. Okay, so there are several examples of this besides seesaw, right? So the beam of balance is a lever, and different concepts can be involved, or basically this can be highly applied in several scenarios. So the basic usage of understanding this principle of moment is only this much, that let's say we need to lift this F1 which is of greater force than F2. So basically we need to design the lever such that the value of D1 is less than D2, or D2 is greater than D. Okay, so what is D2? If you remember, it's about the effort arm. That effort arm should be greater than D1, and then we can apply a smaller force and lift that higher value of F. Okay, so that thing being said, now let us try to understand a new concept which is center of gravity. Okay, so before going into that concept, in very easy terms, center of gravity basically means that point at which we can assume the gravity of the complete mass to be acting up. So basically that is a point from which we can assume that mg is being acted up. Okay, that being said, that was a simple explanation. Now let us try to understand the concept using the illustrations and the iteration given. Okay, so many of you may have experience of balancing a notebook on the tip of the finger, either a notebook, or basically you may have also tried to balance a pencil on the tip of the finger. So basically you have done such sort of things right? So basically what actually happens, there are several. So first of all, let's say I try at this location, I try at this location, but then we try to reduce and finally find a point at which the balance of the pencil is held true. Correct. That point can be assumed as the point at which the force of mg is being acted upon, and we are just putting a resultant value of r such that this r is equal to mg, and hence this pencil is in translational equilibrium. Okay, so why it is basically rotating like this? We can also say why it is rotating, because there was a difference between this value of r and mg, and hence there was a rotational rotation being happening with difference in forces. So basically, there's a moment being observed there. When we keep it at the same location r and mg, so therefore at this location there is no value of because r is equal to mg and there is no distance between them, so the moment of force is zero, and hence we can say that this is in translational equilibrium also and rotational equilibrium. Fine. So I hope you understood this concept. Let's move on. So many of you may have experience of balancing your notebook on the tip of the finger. The figure shown here illustrates a similar experiment that you can easily perform. So take an irregular shaped cardboard and a narrow tipped object like a pencil. You can locate by trial and error a point G on the cardboard where it can be balanced on the tip of the pencil. So basically try to draw a hole inside the cardboard and then try to hold it in vertical position such that there is no delay or no rotation of the cardboard happening. So when this is done, the cardboard remains horizontal at this position, and this point is nothing but called as the center of gravity or the CG of the card. Okay, so I hope this is clear. So basically that point at which we try to hold it such that there is no translation happening, there is no rotation happening, as in the cardboard is being kept horizontal, then basically we say that that position is nothing but your center of gravity CG of the card. Okay. The tip of the pencil provides a vertically upward force due to which the cardboard is in mechanical equilibrium. So basically I just explained you like this. So basically let us say this is R and this is mg. So this is the force due to your pencil. So as shown in the figure, you can clearly see that the reaction of the tip is equal and opposite to mg. So we can see that the reaction of the tip here is basically equal and opposite to this mg. Fine. What is mg? Capital M into small g is basically the total weight, that is the force of gravity on the cardboard, and hence the cardboard is in translational equilibrium. Okay. It is also in rotational equilibrium, because if it were not so, due to the unbalanced torque, it would tilt and fall. So I hope you understood this using this cardboard example also and using that pencil example also. So it is basically intact like this, and it is not even swinging. So basically not even tilting. Fine. So that is a basic understanding of your center of gravity. Moving forward. So there are torques on the cardboard. Now we are trying to distribute this rigid body as an example of system of particles. So there are torques on the cardboard. Due to the forces of gravity like m1g, m2g, etc., acting on the individual particles that make up the cardboard, right? So this can be assumed as nothing but equal to some m1, m2, m3, m4, m5, m6, m7, all acting in this position like this. Okay, so it's like m1g, m2g, m3, m3g, m4g, and so on. Okay, the CG of the cardboard is so located as the total torques on it due to the forces m1g, m2g, etc. is 0. The summation of the torques is basically equal to 0, and that is only why we say that the rotational equilibrium is 0. Correct? So now, first of all, let me explain more. So basically, what is happening here is that total tau g, the total gravitational torque, can be said as equal to nothing but summation of all tau where I is from 1 to n, okay, which is equal to basically summation I is from 1 to n Ri cross mg. Ri cross f is basically mg here, or I can write this to be m1g. mig is equal to 0. Okay, so basically what we can say, we can define the center of the gravity The CG, the CG of a body is a point at which or where the total gravitational torque on the body is zero. Where the total gravitational torque on the body is zero. So what is the meaning of total gravitational torque? Total means the sum of all the system of particles, torque of them, and gravitational torque means the torque which is generated due to the external force, which is gravitational force. Okay. So I hope you understood this example. Now let us try. Let me make you understand one more example here, so that this is that example. So basically, what we need to implement so that we can calculate or find the center of gravity location of your particle or some of a rigid body. Okay. So basically, what we basically do is, let us suppose this is that rigid body. We try to hinge this, we try to tie this rigid body with some point A. So this is how the orientation of the rigid body is. So basically now what we do, as this string is intact, we try to extend this line in this fashion. We do the same for this point B, C, A1, B1, C. So what we basically found, that this is how the axis of orientation is. So again, we basically remove this tie, we keep the tie at this location, and we try to tie it here. So when you try to tie it from this location here, let's say this is your B, then the direction of or the line of intersection is being found like this. When all these different lines are being joined, we found an intersection point of all the axes. This point is nothing but your gravity, center of gravity. Okay. So I hope this complete concept in which we understood. So basically, let me just write that line also here. So here the intersection of all the verticals gives the center of gravity. Okay. So what I basically did, we first took the body, tied a rope at this point A, held at this location. So then, as this was vertical, we just extended this line. So this was the first line we got. Then we removed a tie here. We'll hold at this location. Again, drew it like this. That is, this is point B here. Then again, some another shape would have been formed, and we would have found out this line. This line has been formed. Similarly, this C line is also formed, and the intersection of all these lines is basically your G. Fine. So that is all the concepts we need to understand for your center of gravity. Okay. So that thing is one thing. Okay. Now, one just consideration or one just note, I just need to inform you. Okay. So one just note, there was a concept we understood in the starting of our lecture series, which was center of mass. And here we understood another concept, which is basically center of gravity. Okay. So let me just write this only, that first of all, the center of mass, this center of mass does not depend upon gravity. It depends only on the distribution of mass of the body. Okay, it does not depend on gravity. It only depends on the distribution of mass of the body. Okay. So that is only one note I just need to give to those who are different things. Center of gravity depends on G. We understood how it is being. So basically, the value or the point at which the mg would be acting, just that point will be basically called as a center of gravity. Okay. In majority of the terms, center of mass and center of gravity coincides, but let us say we take the rigid body as to be so large that at different parts or different regions the value of G is different. Then in those case scenarios, the center of mass and center of gravity won't match. Okay. So I hope that line is also clear to you. that CG and CM are different things. COM basically depends on your distribution of body only. It has nothing to do with gravity, but central gravity depends on gravity also. So in general terms, COM and CG can lie on the same point. But if the rigid body is so much large that there's a variation in the gravity, the value of gravitational acceleration, then it may change. Fine. Okay, so that is the ending of this concept, I guess. Now let us understand some of the examples related to all the concepts we studied regarding the rotational and the translational equilibrium. And then after those being done, we'll move on to the most important concept of this lecture series, which is moment of inertia. Okay, so fine. So let's start with this problem first of all. So a metal bar 70 centimeter long. So metal bar 70 centimeter long, okay, and 4 kg in mass. 4 kg in mass. So as it's a homogeneous rod, therefore the weight 4 kg would be acting from the center of gravity. What will be center of gravity? It will be at its center of mass. It will be its center of mass at its geometric center. So therefore, at a location of 35 centimeter from here, there will be a mass, or sorry, a force acting in downward direction, which is nothing but equal to your m into g. Right? What is m here? M is 4. What is g here? So that will refer to the question, how to solve the question. Okay. So let me add it as 4g only, right? Okay. Fine. Next thing is that it in mass supposes 2 knife edges. So these are knife edges K1 and K2, which are placed 10 centimeter from each end. That means this is given to you as 10, and this is also given to you as 10. Correct? Next thing is, so therefore the reaction force would be acting in this direction. So this will be your, let's say, R1, and this will be your, let's say, R2. Okay. 6 kg load is suspended at 30 centimeter from one end. So let us say that load is being kept at this location here. This is that P, which is 6 kg. So it will be nothing but 6 into G. Okay. The distance from here to here is basically given as 30 centimeters. Okay. Question is basically you need to calculate, find the reactions at the knife edges. Assume the bar to be of uniform cross section and homogeneous. Okay. So that is a complete concept. That is a complete dimensional explanation. Now let us directly solve the question and move forward. So what we basically need to do, we just need to use the equilibrium of rigid body concept. So first of all, let's calculate the translational equilibrium of the body or the system. So translational equilibrium of the body. So what will be the translational equilibrium of the body? First of all, summation fx equal to 0. There is no use because there is no force in x direction. Let us calculate now summation fy. Using summation fy is equal to 0, what we can say? We can basically say that this R1 plus R2 is nothing but equal to your 4g plus 6g, because 4g and 6g are in the downward direction, and your R1 and R2 are in the positive direction or upward direction. So therefore we can either write R1 plus R2 minus 4g minus 6g equal to 0, or we can basically write R1 plus R2 is equal to 4g plus 6g. Okay. So therefore this is the first equation we obtained. R1 plus R2 is equal to 10g. Right? So this is the first equation. Now let us consider your so this is your translational equilibrium is being done. Now let us calculate the rotational equilibrium of the body. So if we calculate the rotational equilibrium of the body, let us try to calculate the rotational equilibrium of the body about the point G, that is the center of gravity. Okay, so let me first calculate so let's start from the leftmost portion. So it will be R1 into this distance. Okay, so as it is 10 and as it is 35, therefore this distance will be equal to your 25. So let me write those in terms of your meters. It's R1 into 0.25. In which sense? This is your clockwise. Correct? Fine. Next thing is plus, next thing will be your 6G. Right? 6G is acting at a location. It's 30 centimeter and 35 centimeter, therefore this will be 5 centimeter. So it's 0.05. This will be this time in anti-clockwise sense. So it's ACW. Okay? Plus mg. What will be the distance of mg? Mg will be equal to 0 plus r2 into what will be the distance again? Distance again will be equal to 25 centimeters only. Right? Into what will be the into 0.25? What will be the direction here? Direction will be anti-clockwise. Okay? Which is equal to 0. Right? So we can just put anti-clockwise in one sense and one in one sense. Therefore we'll get R1 by 4 is basically equal to 6G into 5 by 100 plus R2 by 4. Okay. So basically these are the two equations which we got. Now we have two equations to unknown. Just solve this complete result. And therefore after this the final answer we will get is R1 is nothing but equal to 54.88 newtons. And R2 is basically equal to 43.12 newton. Okay. So I hope this concept of how we are doing this to be clockwise, this to be anti-clockwise, this to be anti-clockwise is clear to you, right? If you are seeing from this location, then R1 will give you clockwise rotation. If you are seeing from this location, this P will give you an anti-clockwise rotation. And again, if you are seeing from this location, this R2 will give you anti-clockwise rotation. The anti-clockwise can get to one side and the clockwise can get to one side. So therefore, we have two equations. This is your first equation. This is your second equation. Using both these equations, we can finally get the answer of R1 and R2 to be equal to 54.88 newtons and 43.12 newtons. Okay? Fine. Now let us understand one more example, which is about a wall. So it can be also said as equilibrium of a wall. Okay. So the question simply states that, let me draw the example again. So a 3-meter long ladder. So let us assume this is the ladder. Okay. It's a 3-meter long ladder. That means this is your 3 meter, correct? Which is weighing 20 kg. So where will the weight be shown? It will be shown at the midpoint of the geometric center of this ladder. The geometric center of this ladder will be at some location 1.5 meter in this angled direction. So let's say I write this as nothing but equal to 20 g. Okay, no problem till now. Leans on a frictionless wall. Basically, what is the meaning of frictionless wall here? That means there is no force of external or frictional force acting in this location. Okay, but please remember there will be a normal force acting. Well, let us say that normal force, I am writing that normal force is equal to F1. Okay, so there will be normal force acting. Let me know that normal force is F1. Now, its feet rest on the floor 1 meter from the wall. So that means that this location is given to you as 1 meter. Okay. And next thing is, so its feet rest. So basically this will be nothing but your F2 again. This is your F2. Find the reaction forces of the wall and the floor. So there is nothing given about the forces, the frictional force which will act in this direction. But we need to take it. So if you see clearly, in which way will this ladder go? It will go in this direction. That's why there should be a resisting force acting in this direction. Let me write it as capital. I think it is clear. So because the ladder will try to go in this direction, there should be a resisting force F so that it can be put in equilibrium. This resisting force F is nothing but the frictional. Okay, fine. So that is the understanding of the diagram here. Now let us understand more. Okay, so what will be this height here? This height will be nothing but can be calculated using your Pythagoras theorem. It is nothing but under root of 3 square will give you 9. Minus 1 square will give you 1. So it is nothing but equal to root 8, which is 2 meters. Okay, you got the value of h also. Now just simply do rotational equilibrium and your this thing is translational equilibrium and calculate the result. Okay, fine. So let us calculate first of all the translational equilibrium. So translational equilibrium of the system. Okay, so here first of all let me do summation fx equal to 0. So using this summation fx equal to 0, what did I get? I will get simply that the frictional force F is nothing but equal to F1. This is equation number 1. Okay. Next thing is, let me do summation Fy equal to 0. So if I do equation summation Fy equal to 0, what will I find? I will simply find that the force F2 is nothing but equal to this W weight, which is equal to 20G. Okay. This is the second force I got. Now let me do the rotational equilibrium of the system. So why we are only analyzing using 3 concepts? Because we remember when we are studying about the equilibrium of a rigid body, we understood that for a number of problems, all the forces acting on the body are always coplanar. Hence, we need only 3 conditions to be satisfied for mechanical equilibrium. What are those 3 conditions? 2 is translational, that is summation fx equal to 0, summation fy equal to 0, and the last was the rotational, which is summation of all the moments at a particular point is equal to 0. Fine. So that thing being said, let us calculate the moment here. So the rotational equilibrium is nothing but here. Let us try to calculate the rotational equilibrium about the point. So we can take about any point here. So let us take it about the point this. What we can refer to this point. So this point is nothing but a point. Okay, huh? So why? So what is the basic use of calculating and using a point? We can calculate any point. We can calculate even this point. We can calculate this point. You can see here it is more easy to calculate using this a point. Why? Because for two forces F2 and this capital F, the value of R would be 0. So it is more easier to use it to analyze the concepts if we just take the concept or the moments using this point. Okay, so let's calculate. So it will be about point A. Let me write it is about point A. Okay, so here what we will get basically, we will get F1 into distance. What is the distance here? So as you can see clearly, there are only 2 forces I am assigning. 20G will be in clockwise sense and F1 will be in anti-clockwise sense. So we can put one on left hand side and another on right hand side. So F1 into basically 2 root 2 is equal to 20G into, so what will be this distance here? So if it is 1, so this will be 0.5. This will be 1 by 2. Okay, so from this we can directly calculate F1 value, that is nothing but 20G into 0.5 upon 2 root. So that's how we got the value of F1. As F1 is understood, this is nothing but equal to capital F. And what is F2? F2 is nothing but equal to 20. So we calculated the value of F2 also, F also, and F1 also. Right? Now, what is the value of, what is the question being asked? The question being asked is, find the reaction forces of the wall and the floor. Okay, so here reaction forces are nothing but, first of all, the reaction forces of the vertical wall is nothing but equal to F1. Right, and what is the reaction forces of the bottom wall? It is nothing but equal to under root of capital F2 square plus F square. Okay, so that's how you can find these relations. Also you can calculate the value of tan alpha. That is the portion which is acting. That is the final resultant value with respect to F. That is nothing but equal to your value of F2 by F. Okay, so if you do the mathematics here, finally you will get the value of F1 as nothing but equal to 34.6 newtons. We'll get the value of F also as 34.6 newtons only, and you will get the value of F2 to be equal to your 196 newtons. Therefore, this is the directly calculated. This can be calculated as equal to nothing but 196 squared plus 34.6 squared, which is nothing but equal to 199 newton. Right? And this tan alpha, this alpha can be calculated to be equal to approximately 80 degrees. That is tan inverse of F2 by F. Okay. So I hope I made you understand completely whatever this question was asking upon, and that's how we basically solve the questions regarding equilibrium of rigid bodies. Okay. So just for a quick revision, what we basically need to do, we just need to find the translational equilibrium of the system. So basically summation fx is 0, and similarly we will do summation fy is 0. And after that, we will basically try to calculate the summation of all the moments about a particular point. The point does not matter, but if you do it by any point, the answer would come same. Okay, because the complete system is in rotational equilibrium. Therefore, the moment about any point, the sum of the moments about any point should come out to be zero of the all the external forces which is acted on. Okay. So that being said, that leads us to the conclusion of this particular concept also. So that is the end of your equilibrium of a rigid body also. Now let us move on to the most important concept we need to understand, that is moment of inertia. Okay, so it's again a moment of something. What is inertia? If you remember correctly, in the concepts of laws of motion, we have understood inertia, right? Inertia can be said as something in easy terms in physics, we can say it's nothing but mass. So just an analogy. So before starting an analogy, let me just iterate, and then we can understand more about it. Okay. So what is the basic usage? Why we are doing this? How we are doing this? How we will implement it? What is it is analogous to? Everything will be understood in bit detailing in this complete concept. So let us start this new subtopic, which is your moment of inertia. Okay. So we have already mentioned that we are developing the study of rotational motion parallel to the study of translation motion with which we are similar, right? So we basically find an analogy between the linear motion or basically translation motion and the rotational motion. How? Let us suppose velocity was said to be said analogous to angular velocity, then acceleration to angular acceleration, force to torque, then linear momentum to angular momentum, F is equal to dp by dt. Similarly, tau is equal to tau external is equal to dl by dt. Right? F external is equal to dp by dt. Tau external is equal to dl by dt. Right? So that thing being said, now let us understand more what is written here. So we have yet to answer one major question in this connection. What is analogous to the mass in the rotational system? Mass is not the same. There has to be some change because there has to be some analogy to be made here. Right? We shall attempt to answer this question in the present section. So now let us understand what is the analogy of this mass and rotational motion. So to keep this discussion simple, we shall first consider rotation about a fixed axis only, which we are already discussing in this same context only. Let us try to get an expression for the kinetic energy of a rotating body. Okay. So here we know that for a rotating body about a fixed axis, each particle of the body moves in a circle with a linear velocity given by the equation v is equal to r omega. So I think this is already known to us that velocity is nothing but equal to r omega. Okay. So therefore, for a particle at a distance from the axis, let's say I make the diagram like this. Let's say this is that rigid body being talked about, and there was this particle P which was being rotating in this circle, let us suppose, and say this is the position vector R, this is the velocity V, and it is moving with angular velocity omega, and we can say V is equal to R omega. Therefore, for a simple particle, also for a single particle which is at a distance Ri from the axis, we can simply say that the velocity of that particle is nothing but equal to R1 into omega. Correct? Now, let us calculate the kinetic energy of the motion of this particle. Okay. So, what is kinetic energy of the motion of the particle? Kinetic energy is nothing but equal to half m1 mi vi square. Which, so in the place of vi, what we can write? We can write vi is nothing but equal to r omega. So, therefore, this can be written as equal to half mi ri square omega square. Clear till this position? Okay. Now let's move forward from this position. Okay. So now let us calculate the total kinetic energy. So the total kinetic energy of the body is given by the sum of the kinetic energies of individual particles. Sum of the kinetic energies of the individual particles. Correct? So therefore what we can write? We can basically write the total kinetic energy K is nothing but equal to summation of Ki, right? Where I is from 1 to n, where I is from 1 to n is nothing but equal to half as mass summation mi ri square omega square. Please look at this very carefully now. Okay, so what we basically did, we basically summed all of them, and therefore we found out that is equal to half into summation I is from 1 to n mi ri square omega square. Okay, here n is the number of particles in the body, but as we know that omega is same for all of these particles, so we can take omega out of the sum. So basically what we can find, we can write as half omega summation I is from 1 to n. Please look at this carefully. It's mi ri square. Okay. Now we will define a new parameter. Let us define a new parameter which characterizes a rigid body, which characterizes a rigid body, which is called as moment of inertia. Moment of inertia, which is denoted by capital I, and it is given by I is equal to summation I is from 1 to n mi ri square. That is the definition of moment of inertia. Okay, fine. So using this concept, what we can write? Therefore, we can write kinetic energy is nothing but equal to half I omega square. The kinetic energy of a rotating body is equal to half I omega square. Look at this equation very carefully. If you remember the equation for linear translation motion, what is that equation? It's half mv square. Each and every concept, each and every product is basically analogous to another concept. So half is basically half only. I is basically an analogous to mass, and omega is analogous to velocity. How? And that's how we found the analogous value of mass with respect to rotational motion, and hence that is the definition of your moment of inertia. Okay. So here, so in kinetic, in linear momentum, in translation motion, basically the m is the mass of the body, v is its velocity. So we have already noted the analogy between angular velocity omega and linear velocity v. It is thus evident that this parameter, which is moment of inertia I, is the desired rotational analog of mass. Okay. So I is the rotational analog of mass. Okay, fine. Now I will take your time. So now it's I think the next 15 to 20 minutes from this lecture and some next lecture will be based upon understanding how to calculate this moment of inertia for different shapes. Okay, so let's start with the first shape, that is let me just add a slide, and let's start calculating the moment of inertia of first of all rod. Okay, so just give me 1 minute. Okay, so first of all let us calculate so here rigid massless rod of length L is given to you, and there are, okay, so this is a different question. Wait, let us first calculate. Let me first make you calculate the moment of inertia of a thin rod of length L. Okay, so the complete mass of this rod is being homogeneously divided into different parts. Now let us try to calculate its value, assuming that the axis of rotation is at its center. Okay, so this is the value of omega, right? This is the value of the complete length as it is at its center. So this is L by 2. Okay, this is also L by 2. Fine. Let us take some mass dm located at this location, right? And now let us try to calculate. So therefore the position of this will be at some location r, correct? Okay. So now in the reference frame, just give me 1 minute, let me just explain how to explain you. Okay, so now we know that what is moment of inertia. Moment of inertia in the, as we have just explained you, that moment of inertia is nothing but equal to summation mi square, right? So in the inference of your differential form, what I can write? I can write it as basically, so I can write that this di is nothing but equal to your dm r square. Okay. Now here, please look at this very, very carefully. So what is what is the complete moment of inertia? The complete moment of inertia is nothing but the integration of r square dm. Okay. Now for this rod, dm can be said as equal to mass per unit length into dr. Okay, try to understand this very, very carefully. So mass per unit length into dr. So basically dm is nothing but equal to mass per unit length into dr. Okay, because we are focusing, so this is nothing but your dr. This small location is nothing but equal to your dr. Okay, so mass per unit length. So basically what will happen? So for a very small quantity, we are trying to find out what is the mass. Now, what is that quantity? That quantity is dr, so we'll multiply it by dr. In another unitary form, what we can write that, okay, so I had some mass, right? So some length L was having some mass M, correct? If some length M was having some mass M, then what will be the mass which dr will calculate? Dr will have a mass which is equal to M by L into dr, which is nothing but dm. Okay, so I hope you understood how we calculate the value of dm. Making you understand again, so basically some length L was having mass M, then amount of mass which this dr would have will be nothing but M by L into dr. Fine. So just substituting this into here, we will get integration r square M by L dr. Correct? What will be its position? What will be r range? R range will go from minus L by 2 because it's a displacement vector, so it's minus L by 2 to L by 2. Let us try to calculate it. As M by L is constant, we can directly put it outside the integration. So it is nothing but M by L integration minus L by 2 to plus L by 2 r square dr. What it is equal to? It is M by L r cube by 3 moving from L by 2, basically it's minus L by 2 to plus L by 2. Just put the values here. What you will get? You will simply get this as equal to r cube by 8 minus L cube by 8. Okay. If you will just solve this, let me solve it and write the answer here. You will get this is equal to I is equal to 3 will also be here. So it's M by 3L into L cube by 8 into 2. Correct? 2 will cancel with 4. Therefore, the final answer you obtain is equal to ML square. L will get cancelled with this. So it's ML square by 12. And hence this is the moment of inertia of a thin rod which has a unit mass, which has a unit, it has a mass per unit length as, let's say, dm or M by L. M by L can be said as mass per unit length. Mass per unit length. Okay, so it's mass per unit length. So the moment of inertia of a thin rod having the mass per unit length as m by L, or let's say note it as rho, is nothing but equal to ml square by 12. So basically we derive this equation, or basically we derive this moment of inertia. So maybe a little bit hectic because it is involving majority of the integration concepts, some concept of DM also. So I will try to revise this again in the next lecture, and then we'll try to derive everything which is written. We'll try to derive this also. We'll try to derive this, derive this, derive this, derive this, derive this, derive this, derive this. Maybe this is not required. We will just go with the understanding of rings, spheres, disc, rod, and rod is being completed. Spheres, disc, and rod. Okay, so let me stop it here only. The final conclusion is we understood that there is a rotational analog of this concept also, which is moment of inertia, and we have clearly calculated the concept of calculation of moment of inertia for a thin rod, which is nothing but about its center, the rotation about its center, which is equal to ml square by 2. Okay, so that thing being said, let me stop the discussion here only. We will move on with further discussion in the next. So the course progress for you, we have completed the introduction, center of mass is completed, motion of center of mass is completed, linear momentum of a system of particles is completed, vector product of two vectors is completed, angular velocity and its relation with linear velocity is completed, torque and angular momentum is completed, equilibrium of a rigid body is completed, and currently we are on the 9th subtopic, that is moment of inertia. Okay, so let me stop the discussion here only. We'll move on with the further discussions in the next part of this lecture series. So thank you so much.